Hello, math friends. This is Mrs. Steele Precalculus section 12.1 notes, day 2. At the end of yesterday's notes, we looked at that kind of funky graph of sine of pi divided by x and talked about how the limit did not exist because as the function approached 0, something different was happening on the left-hand side that was happening on the right-hand side. And that is the situation where a limit does not exist. So right now we're going to look at 3 more examples of situations of graphs where the limit fails to exist. So in our first example, we're going to have a function here, and this is just going to be a function that has some horizontal lines. You've seen these before. We call these step functions. So let's say we've got a horizontal line right here, but it stops right there at 1, and then it jumps up here and then continues from that point there. So this is a picture, like I said, of a step function where the graph f of x has a jump at the value x equals 1. And the limit here as x approaches 1 does not exist, because as x would approach 1 from the left-hand side and as x would approach 1 from the right-hand side, we would have 2 very different values for our function. So this is a situation where left and right limits do not agree. And if the left and right limits don't agree, the limit does not exist. In our next example, we're going to think back to that graph that we were looking at, the sine of pi divided by x. This one has the same idea to it. We've got some sort of a graph that is oscillating, and on one side of x equals 1, the graph is above the x-axis, and on the other side of x equals 1, the graph is below the x-axis. And again, when we're looking at the limit, we're focusing on what's it doing right around that value, x equals 1. And so if the graph is oscillating at x equals 1, our left and right limits do not agree, and the limit does not exist. The last example where the limit fails to exist would be a graph that has a vertical asymptote at a particular x value. So I'm going to say that my graph has a vertical asymptote right here at x equals 1. And on the left-hand side of x equals 1, my graph looks something like this. And on the right-hand side, my graph looks something like that. Okay. So as you can see, on the left-hand side of x equals 1, the graph is shooting up to infinity. On the right-hand side of x equals 1, the graph is shooting up to infinity. So you might think, well, the limit appears to be infinity, right? So let's write this down. Left and right limits both go to positive infinity, but the limit still does not exist. And this is because there is no limit, right? Infinity is not a limit. Infinity is infinity. So we could say the limit does not exist because there is no limit. For situations like this, we will often look at one-sided limits, okay? So you can either look at values from one side or from the other side of a given value of a, either from the left side, or whoops, sorry, one side of the given value of a. So you can either look at the left-hand limit or you can look at the right-hand limit. And we have notations for this. Our left-hand limit, we would say as we approach a, and we put a little negative sign. And our notation looks like this. The limit as x approaches a with that little negative sign. And that means as x approaches a from the left-hand side of f of x equals L. The right-hand limit then is a little a with a plus sign. So we would say here, the limit as x approaches a from the right of f of x equals L. So for a left-hand limit, you're always going to be selecting x values that are less than a. And for the right-hand limit, you're always going to be selecting x values that are greater than a. We've been using this language already when we've been talking about limits, but now we're kind of putting a formal definition of a left-hand limit and a right-hand limit to it. So when you look at the picture here of that first example, this is the example 1 that we kind of drew before. In example 1 here, the limit as x approaches, and I know it says 1, but really based on the picture's a little bit off. This should be 0. So as x approaches 0 from the left-hand side, the limit of the function appears to be 0, right? Because we're looking right here. But then the same picture as x approaches 0 from the right-hand side, the limit of our function appears to be 1. Okay. So we would say that the left-hand limit is 0. We would say that the right-hand limit is 1. But we would still have to say, so I'm going to put a little note down here, we would still have to say that the limit as x approaches a of f of x dne does not exist. And this is because the left-hand limit and the right-hand limit do not agree. So then, when does a limit exist? A limit exists if and only if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x. In other words, the limit exists if and only if the left-hand limit equals the right-hand limit. So for our last example here, we have a picture of a graph given to us, and we want to try to use the graph to try to find the values of the following if they exist. Okay? So for letter A, we want to find the limit as x approaches 1 from the left. Well, as x approaches 1 from the left, so if we're looking at our graph, we're talking about right there, the limit is getting closer and closer and closer to -1. Okay? And then as we approach 1 from the right, the limit is getting closer and closer and closer to -1. The value of f of 1 is actually down here, right? The actual value of f of 1 is -3. But we've talked about this now many times. It doesn't matter what the function equals at 1. It only matters what the function is approaching as x approaches 1, right? As x is approaching 1 on the left, it goes to -1. As x is approaching 1 on the right, it goes to -1. The value of f of 1 is actually -3, but for part D, the limit as x approaches 1 of f of x does equal -1. Because the left-hand limit and the right-hand limit equal each other. So now let's take a look at another situation on the graph. Letter E wants us to take a look at the limit of the function as x approaches 7 from the left-hand side. So from the left-hand side, as x is approaching 7, the value of our function appears to be approaching 2. Then if we look at the limit of f of x as x approaches 7 from the right-hand side, we're down here, and the function appears to be approaching -3. Well, what is the actual value of the function at x equals 7? The actual value of the function is -1. But the limit as x approaches 7 of f of x does not exist. And this is because the limit as x approaches 7 from the left-hand side of f of x does not equal the limit as x approaches 7 from the right of f of x. Or in other words, the left-hand limit and the right-hand limit do not agree. So right here, our left-hand limit does not equal our right-hand limit.